And away we go. So, you may be aware that yesterday was Earth Day, and that today there are protests taking place all over the world, mainly led by young people, at climate inaction. About the way to put this, I think, in the simplest terms, is that the Intergovernmental Panel on Climate Change, the UN body tasked with studying and reporting on this on a regular basis, issued the third and final volume of what may be its sixth and final report less than a month ago. And it concluded that if we don't change course drastically this decade, which we are now a quarter of the way through, we will not be able to contain the damage that we are doing to our planet. And so, unlike what I've done in the past, which is to give you an occasional lecture or an occasional update on this topic, I've decided, given on the one hand the urgency, right? We are on the brink of releasing catastrophic processes that when they begin, we don't know where they end and how to control them. So that's the urgency. We are potentially, as a matter of fact, quite likely, doing things today that, if we continue to do them, will cause the extinction of our species and perhaps natural life on this planet. And on the other hand, complexity, right? That anybody who tells you they fully understand this has a God's eye view on the world that none of us mere mortals have. Right? This is tremendously complicated. I am not a climate scientist. I have spent several years trying to come up to speed on this topic because it is so urgent that I feel like I need to be able to speak about it in a way that I hope sheds some light on it. And so we need some time to see it from several different angles at once, from a climatologist scientific angle, to understand the processes, their interconnection, the ecosystems in the Arctic, in the rainforest, with the permafrost and the tundra, in the oceans, and the ways in which they interact. I'll begin that today, but this is something that it takes time to unpack, to see the full complexity. But we also need to understand the technology, the ways in which we have put carbon dioxide, formerly buried in the earth, into the atmosphere, and what that is doing, but also the technology that allows us now to perhaps sustain something like the civilization we are accustomed to without continuing to do that. At least that makes that conceivable, even if difficult. And then also to focus on both the ethics and the politics of this. What does it say about us that we are prioritizing maintaining our current way of living, our energy intensive civilization, when we know we can certainly anticipate the risk that if we don't change course, and change course quickly, the consequence is going to be that future generations will not enjoy anything like the way of life we are accustomed to. Is that not a matter of intergenerational justice and ethics? And finally, of course, there's a political dimension to this. I imagine, speaking with you today, I am mainly preaching to the converted. We know this is an emergency. We want action taken, and yet it's not being taken, right? There was a lot in the Build Back Better bill that would have done a lot in the United States to put us on a better course, and we couldn't get that bill through Congress. Joe Manchin, among others, stood in the way, in part because of the climate change provisions. And of course, even if we pass that bill, if China, India, Brazil, Malaysia don't act, if Europe doesn't act, if heaven help us, Russia doesn't act, we are not going to solve this problem. So the politics of it are almost as complex as the science of it. And so rather than presenting a single lecture on this topic, I'm proposing that we spend 4 weeks together discussing what I'm calling field notes from a world on fire, looking at first the overall process that is heating the planet. Second of all, what that is doing to biological life and complex ecological systems on the earth. Third, what the technological and economic implications are for changing course, and why it is so far we appear to be incapable of making that correction. And then fourth and finally, really focusing on the politics, looking at what a just and effective response would look like, and alternatively, what kinds of responses we are going to be forced into if we cannot mount that response, right? And here I'm talking about geoengineering, which we have talked about before. The idea of for instance, putting a tint on the windows we're increasingly rolling up on the planet, by which I mean putting reflective material into the upper stratosphere to keep the sun's energy from ever reaching our atmosphere or the Earth's surface. And I want to suggest to you, as you will hear later, that this is an enormous gamble. Every time we try to re-engineer nature, we discover unanticipated consequences. It's very often the case we really don't understand how an ecosystem operates until we have done irreversible damage to it, and then see, oops, that's the part we didn't understand. We are on a course right now where we will be required, in order to save our lives and save the planet, to fundamentally alter some of the most important dynamics that have sustained life on the planet up until this moment. I would suggest to you that that is a huge gamble that we should do our best to avoid, if at all possible. So 4 lectures covering at least 4 facets of the problem. Let's get started. And as I have said, today I want to talk about the science, and I want to just give a brief indication of why I've titled the lecture "The Complex but Certain Science of Global Climate Change." And the complex part is something that any climatologist who is being honest openly avows. The processes, right, at stake here, the ocean currents, the jet stream, the interaction between the humidity that the surface of the ocean generates as it interacts with those jet streams, and the reflectivity of the atmosphere as a whole, as more or fewer clouds enter our stratosphere, the way in which the ocean currents affect the melting but also formation of glaciers on the poles, the way in which rainforests are formed, maintained, and destroyed, the way in which the permafrost reacts to the increases in temperature on the planet, These are enormously complex processes, each taken on their own, but they are all interacting with each other. And so we don't fully understand this. And humility is in order, right? To take an example that we're going to spend some time on today, when we looked at the pace at which we thought the ice caps would melt 20 years ago, we thought we probably had 100 years. It turns out that major Antarctic ice fields started disintegrating exactly at the time that Al Gore was telling us we had 100 years. The problem is not with Al Gore or even the science of the time. Yes, we misunderstood, and what he learned from the scientists he based his work on was inaccurate and far too optimistic. Nevertheless, the problem is with the complexity of the subject matter itself. And so we need to be humble. We need to understand that these processes that we are unleashing interact with each other in systems that we do not fully comprehend, that may in fact be so complex that there are important elements of randomness and unpredictability in them, and therefore the cautionary principle: be careful starting events that you don't know exactly how they're going to turn out. Do your best to avoid catastrophe is the appropriate principle. But having said all of that, I also want to emphasize the second main operative term in the title: the certain science of global climate change. And here, at a simple level, putting more gases into the atmosphere that trap the sun's heat and energy skews the planet's energy budget, makes the planet retain more heat and energy, and in so doing interferes with all of these delicate ecological processes. Among the races that this has unleashed is the race to understand the details of how this operates. And we're not there yet. That's why we don't just have one UN report on climate change, but reports every 6 to 8 years, because as the science advances, as we gain more evidence, as the process of climate change itself accelerates and enters new phases, we come to have a better understanding. Please note that the computational power that we have now, between much faster super processors, so much better computers, and the development of artificial intelligence, means that we can simulate future climate change and the interaction of different ecological processes much better today than we could 20 years ago. But having said all of that, the central idea is certain: human activity is increasing the concentration of heat and energy trapping gases in our atmosphere, and that is slowly heating the planet. We are about 1.1 degrees Celsius hotter in terms of the average temperature at the surface of the planet in 2021 than we were in 1850, before the Industrial Revolution started pumping all of these gases into the atmosphere. There's a precise number that the UN uses: 1.07 degrees of that 1.1 degrees is anthropogenic, caused by human activities. But again, that might exaggerate the degree of certainty. What is certain is that the planet is warmer and that we are causing it, and that if we continue down this path, our future looks a lot like this Bosch painting of hell a world on fire. When I say that, please note you are well aware, painfully aware, that fires are burning right now in Texas and New Mexico and Arizona and Colorado. Please note it is April, not August. The Western fire season used to begin in August, used to burn for a couple months. This is, as the Colorado governor said yesterday, absolutely unprecedented to have this kind of burning at this time of year. This diagram is not from the present. Please don't be alarmed in thinking that Northern California is on fire right now. This is from last summer, but as you can see, and again, it's an artist's representation. It's not literally all of these fires were this large at one time, but clearly the Western United States is drier and hotter for longer. And the result is that it is burning in fires that are more ferocious, more destructive, occur over a longer period of time, and take up larger swaths of land. It is testing close to overwhelming our capacity to fight these fires. They are tremendously destructive. This is a portion of the world on fire. We can pan out and look at the continent of South America. This is again data from the previous fire season. And as you can see, again, an artist's rendition, this time using satellite imagery to try to show all of the places where fires burned uncontrollably in the last fire season. And particularly concerning is obviously the Amazon basin, the so-called lungs of the world, the place that generates the most oxygen, captures the most carbon dioxide of any place on land on the earth. And it is being slowly destroyed, slowly, on the one hand, converted to farmland with slash and burn farming techniques, and on the other hand, turned into savanna or desert by hotter temperatures, decreased humidity, longer summers, drier winters, and not just the composition of the atmosphere, but also the large scale weather patterns of North America and Western Europe depend upon the Amazon putting oxygen and humidity into our atmosphere. If this continues, Western Europe, North America are going to be very different places in the future than they have been for the last couple hundred years at least. And we can shift continents and look at Australia, again, an artist rendering of the terrible fires that occurred in Australia a couple of years ago that whole ecosystems have still yet to recover from. Same phenomena at stake here, right? In part, this is something we have compounded by containing fires, not allowing controlled burns to occur so that more and more combustible fuel accumulates. It is something that is then compounded by the spread of dry lightning into more and more areas as the atmosphere gets more energy from the sun as it is retained by greenhouse gases. But this again is evidence of a world on fire. And so this is data from NASA, and it shows from 2018 to 2019 the extent of the fires on a global scale. And it's a little hard to reconstruct with great precision, but as far as we can tell, this is the worst fire season we can detect. And we're doing our best to go back 10,000 or more years to trace the record in the ice core or in tree rings or in the tundra of permafrost, right? And so again, evidence, as I put it, that the world is on fire. These are mega fires. They move 50 miles an hour. They jump miles at a time. They do tremendous destruction. They're really a different kind of fire than the fire of the previous centuries, for which our firefighting infrastructure is built. And so the world is changing more quickly than we are able to keep up with. Really, a world on fire is a metaphor, right, for the idea of extreme weather. As these fires hit these forests, they destroy the forests, right? The trees, which take carbon dioxide, a heat trapping gas, out of the atmosphere, exchange it for oxygen, something that sustains life on the planet, and does it through photosynthesis, right? They are being burned and killed. As they burn, they release more carbon dioxide into the atmosphere. And these fires are so hot that they are melting the minerals in the top soil, producing essentially magma. And then, as a result, the magma prevents, well, it hardens into rock and prevents new trees from growing, right? Controlled, regular fires are actually healthy for forests. Mega fires are incredibly destructive for forests. This is the first time where we will begin talking about a self-reinforcing cycle. The planet gets hotter and drier. The result is the forest fires become more extreme. The forest fires put more carbon dioxide into the atmosphere, further heating the planet. And the fires are so hot that the forests cannot regenerate over time. So more of that carbon dioxide stays in the atmosphere for longer, making it hotter, making it more likely that there will be more severe fires in the future. And now we're in a loop where if we don't break one of the cycles of the loop, this potentially spirals upward again and again. As I said, right, fire is a metaphor for extreme weather. And of course, extreme weather takes multiple forms. We had 2 years ago the worst Atlantic hurricane season ever recorded. These storms, this is Hurricane Maria over Puerto Rico, are more energetic, right? That they're bigger, their winds are more powerful, they cover more territory, they sweep up more humidity than storms have been in the past, because the temperature on the surface of the oceans, which gives these storms its energy and humidity, is hotter than it's ever been. A doctor who went to Puerto Rico in the aftermath of Maria to help out took this image, which he shared with me. These winds were so fierce, they picked steer up, threw them 20, 30 feet in the air, and then they landed in telephone poles. And of course, the destruction is human as well. As you can see, houses destroyed, people having to wade through waist deep toxic water. This is another aspect of the altered world we're living in. This is a heat wave that set in over the subcontinent, India and Pakistan, in 2019, shattering records, right? The temperatures here, 50 degrees in Celsius, up into the 130s in Fahrenheit, kind of Death Valley type temperatures that completely dried out water holes that villages relied on, that melted asphalt. The human body cannot sustain this kind of heat for long. We're talking about a part of the world with weak infrastructure that doesn't have good water supplies, let alone air conditioning. Again, one way to think about this is that we're living in a shrinking planet, not literally, but in the sense that if the temperature continues to rise, the portions of the planet that will be habitable regularly, year round, year in, year out, will be fewer and fewer. And so we are going to be crammed into less space if we continue to have the number of human beings that we do on the planet. Last illustration of this, you may have heard that Durban, South Africa last week had major floods, at least 400 people dead, but I suspect the death toll is going to go up significantly. Areas that had monsoons but never had flooding like this before. Again, there's more humidity, there's more energy. This is not the typical rain season for this part of Africa, and yet these floods literally buried houses under 40 feet of water and mud with seconds or minutes of warning, no way to get out of their path. Again, a different kind of world we're living in. So, with that in mind as an overview, let me try to synthesize in more systematic, less pictorial terms what it means to live in a world on fire, right? A world in which it is getting warmer. It has already got more than 1 degree Celsius warmer, and it is certain to get another half degree warmer by the end of this century, if not sooner. And that is the most optimistic scenario, much more likely that we will get another degree Celsius or more hotter. And at that point, all kinds of changes will occur, which will make this a much less habitable, much more dangerous planet. So the first thing to see, right? It's not just that there are bigger fires that are faster and more destructive, that whether it's flooding or mudslide or hurricanes or ice storms, whether it's the Arctic dome escaping from the Arctic region and coming all the way down to Texas, we are going to have crises, right? And the thing that I think we need to recognize is they're not going to wait for us to recover. They will come in rapid succession or simultaneously. And so the world that we live in is going to be increasingly vulnerable as a result of the processes we have unleashed. Similarly, we will increasingly have more and more of these self-reinforcing cycles in which climate change causes events that cause more climate change. The example I've already given, the burning of forests. Another example, the melting of the ice caps. That's just the beginning, right? There's methane stored at the bottom of the ocean that's going to be increasingly released as the oceans warm. There is methane and carbon dioxide also stored in the permafrost that will be unleashed as it melts. And the result is going to be that if we are not careful, these cycles will continue to reinforce each other, and we could very easily end up in a place where we get runaway climate change, where the processes can no longer be controlled by us, no longer be reversed or even mitigated by us. That is, and I want to be as clear as possible, right? The reason I want to do 4 lectures is I want to share the hopeful information with you. And there is genuine and hopeful information about technological changes, about movement in the right direction, about our capacity to solve this problem, which is growing as the problem grows. But we need to have a clear-eyed view of the dimensions of the problem as it exists now and the potential for it to get much worse if we do not begin acting immediately. And so the next thing to notice is if we continue down the path we are on, it will increasingly be the case that we unleash events that we lack the capacity not only to control, but to cope with, right? That the fires are going to burn uncontained, that we're not going to be able to assist people who have been cut off from electricity and clean, potable water by these mega storms, that the droughts are going to deprive people of food, create famine, and we're not going to have the capacity to alleviate the starvation and suffering that it generates, and that civilization will fray as a result. One of the studies that's getting some attention now suggests that as we cope with hotter temperatures, we are becoming less patient and more aggressive. That this is a fairly natural tendencies. You actually see more fights, more violence in hotter climates, especially during the hotter time of year, because it tends to make people's fuses shorter, their temperature burn hotter. And so again, this will potentially uh, interfere with the accomplishments of civilization and hence our capacity to cope. So what we know increasingly is that we are unleashing processes that we cannot understand. What the most recent report from that intergovernmental panel on climate change that the UN assembles and charges with producing those reports, the one that was just published in March, says we have to act this decade. We have to, in the 7.5 years remaining in this decade, get to zero net carbon emissions to avoid this, right? And to be clear, right, the planet has a capacity to absorb carbon. So that doesn't mean we can't ever fly a plane, drive a car, burn wood again. What it does mean is that we cannot exceed the amount we put into the atmosphere. The amount we put in the atmosphere cannot exceed the amount the planet can absorb in 7 years if we want to keep the heating of the planet below 2 degrees Celsius. In other words, below the threshold of likely global catastrophe. We have to act now. And so the question is, can we do it? Can we do it intelligently, deliberately, effectively, and globally, right? If we do it and other countries don't, if other countries do it and we don't, we're not going to accomplish what we need to do. And can we do it while preserving our civilization and our most important values? I believe we still can. I believe, on the other hand, that we have failed up until this point. And it's why there are protests happening around the world today, right? Because especially people under 30 are looking at people like us and saying, you've known about this for 20 years or 40 years, and yet you have failed to take the appropriate steps. And the result is that people like us will bear the cost. We don't know if the planet will be habitable for the remainder of our lives, let alone our children or grandchildren or their children's lives. This is where the sense of urgency, outrage, and I hope political capacity will come from. All right, so with that overview in mind, I now want to provide a little bit of the scientific background. I am not a climate scientist. I've done my best to understand this. I hope what I say will make sense and be accurate. Please feel free, as always, to ask questions as they arise. Don't feel like you need to wait for me to come out of the slideshow. Just unmute yourself and ask away. So I think that the central concept here, two of them really, is the greenhouse effect and the Earth's energy budget. And to be as clear as possible, the greenhouse effect is not a bad thing, it's a good thing for our planet. Our planet does not heat itself, does not generate the energy necessary to sustain life, to move the atmosphere around, to generate the current in the oceans, right? That comes from primarily the sun's energy hitting our planet as it moves out from the sun into space and being retained to the right degree by our planet. And this then gets us to that second concept, the Earth's energy budget. Of the earth, the energy that we get from the sun, we can use roughly 2/3, 3/4 of it. We need it. We need it to keep our planet at the right temperature for us and biological life and our ecosystems to thrive. But on the other hand, there's around a third of it, around 30% of it, we don't need. And it is reflected back out into the solar system. And there are complex processes that tend to maintain an equilibrium in which the amount of energy we're getting is the amount of energy we can use, the amount of energy we reflect out maintains a relatively stable climate on the planet. Just like when you're doing your personal budget, you figure out what your revenues are, you figure out what your expenditures are, you adjust so that the two roughly equilibrate. Hopefully, you can save a little bit. And similarly, with the Earth's energy budget, if we're in an equilibrium, then we basically maintain a stable temperature for the planet and a whole bunch of other processes connected to the energy that we are getting from the sun. This is complicated, too complicated for me to fully understand, let alone explain, but it's much more complicated than the diagram I just showed you, right? And so to give a couple of examples, on the one hand, um, as the sun's energy comes into the atmosphere, some of it hits clouds, clouds push it back out into the atmosphere. As, by the way, more energy from the sun gets through to the surface of the planet, it heats oceans, lakes, etc. More water evaporates, there are more clouds, more energy gets pushed away, right? That's one of those equilibrating mechanisms. Similarly, if more energy gets to the surface of the Earth, it turns out that the surface of the Earth then radiates more energy back out into the atmosphere, and some of that ultimately leaves the Earth through the stratosphere out into the galaxy as well. And without going into the details of this, I do want to just mention that, right, photons, the Earth's energy travels to us in waves, and different molecules interact with the waves or the wavelengths of sun's energy in different ways. And so it turns out clouds are actually among the most effective heat trapping gases, but they don't capture all of the wavelengths of sunlight. Some of it cuts through the clouds and goes right back out into the atmosphere, except carbon dioxide captures some of the wavelength that clouds don't capture, right? And so one of the things that we have to pay attention to is the composition of gases in the Earth's atmosphere. And really, for the last 150 years, human beings have been altering the composition of our atmosphere, especially increasing the parts per million of carbon dioxide. I'll show you in a moment how much that has gone up, but also increasing methane and other gases in the atmosphere. And as a result, we have thrown the energy budget out of whack. I know I've shown you this diagram before, just very quickly, right? As opposed to the standard equilibrium in which the amount of energy being radiated out into space is stable, and so the temperature stays stable. As we have increased carbon dioxide and other greenhouse gases in the atmosphere, the Earth is retaining more heat. That means, right, that the Earth's temperature is increasing about 1 degree Celsius over the last 150 years. Now, how do we explain why we're putting more carbon dioxide into the atmosphere? I think the first thing to notice, and again, I've shared this information with you, it should be at this point familiar, but I think it's worth looking at for just a moment because it's such an astounding diagram, right? The human population on the earth was in steady state at around 4 million for most of the last 10,000 years, right? And with advances in civilization, agriculture, slowly the invention of states, our population increased to almost 200 million by the time Christ was born. And then to around 750 million at the beginning of the industrialization process. But note that it's more than 10 times that high today. And almost all of the exponential growth is concentrated in the last 100 years, even in really the last 50 years, where we've gone from 3 billion to approaching 8 billion people. And in order for us to house, feed, sustain this many people, keep them reasonably healthy, we need to create a lot of energy. And that is to transport goods to those people in urban areas that live far away from agriculture, to generate electricity, to do what we're doing right now, but so many other things, including air conditioning and heating, so that we can survive on a planet with more extreme weather. We produce a lot of goods in industrial production methods that take a lot of energy. And we have replaced traditional agriculture with industrial agriculture and monoculture. And that allows us, thanks to the Green Revolution, thanks to fertilizer and pesticides, which are petroleum products, of course, to feed billions of people. It simply wasn't possible 100 years ago to feed the number of people that are on the planet today, but it is energy intensive to do this. And so we have an energy intensive civilization, and our primary source of energy is petrochemicals. Oil is the number one, followed by coal, followed by natural gas, right? And so as a result of extracting all of these carbon-based fuels that were deposited in the surface of the earth over millions of years by normal processes of decomposition and compression, we have learned over the last 150 years to mine coal, to extract oil, to refine it and deliver it and burn it in internal combustion engines. We are feeding, housing, keeping safe billions of people, but we are doing it at the expense of treating the Earth's atmosphere as if it were a garbage dump for our exhaust. And it is unsustainable. It is like rolling up the windows in your car on a hot day in the sun with no air conditioning on. We are going to cook ourselves and the planet if we stay on this path. It is true, and this is the good news, that non-carbon based forms of energy have really become technologically viable, especially over the last decade, and that they are beginning to be a significant part of the mix of the energy sources we use. It's actually the case that wind energy was the most important source of electricity in the United States last month. But having said that, you can see the disproportion at a global level. We need to fundamentally alter the mix, have what's called an energy transition in the next 7 years if we are going to solve our problems. Very quickly, historically, we know who is responsible for the most emissions. Even today, the United States per capita has more emissions than any other place in the world. When we look at this historically, the developed world is by far and away responsible for the most emissions. The 20 richest countries in the world produce still today about 80% of the carbon dioxide emissions. You can again break this down instead of overlapping it country by country by country. It is the case that China and India and the developing world are now starting to industrialize, and as a result, are also contributing to the problem. As a matter of fact, China is the worst emitter of carbon dioxide in the world today, but this is something that has developed very recently, whereas the United States has been at it for a long time. And frankly, we have reaped the benefits of it in terms of our wealth. If we're going to have a fair solution to this problem, we need to recognize the disproportionate contribution that we have made to it. And when I say a solution, we have started, right? Before Paris, we were on our path to a world that was 4 degrees Celsius hotter, a world in which essentially human civilization and life collapses. Now we're on our path to a world that will be certainly 2 degrees hotter by the end of the century, a world that will shrink, become more disorderly, more chaotic, more prone to extinction. And we need still to change course. We need to get to here, right? And this is the challenge. This is something that has never been done before in human history. The phrase here is energy transition, to get from a place where we're using carbon-based energy to a place where we are not. Previously, every energy transition in the world has been additive. We put more kinds of fuel in the mix without subtracting the old stuff. We used to rely on wood. We still rely on wood. Now we need a subtractive energy transition. We need to decarbonize our economy. This is going to be expensive. This is going to be difficult. This is going to be perhaps the most important challenge the human species has ever faced. I am convinced that we can do it, but we need to be focused on the dimensions of the problem, the severity of the threat that failure represents, the need to change our lifestyles and to work together if we are going to do this. These are the largest emitters. You can see how much China would need to change. You can see how much the United States would need to change, how much Europe would need to change. We need change fast to meet the goals that the UN has set for us. This is just the evidence about what's happening with temperatures again, right? Beginning in the middle of the 20th century, we see a little dip with World War II, but then just a straight upward trajectory, right? We see this on a longer time scale, and this way you really see how extraordinarily exceptional the last 50 years have been. And this is right, the really important diagram. This shows planetary correlations between carbon dioxide levels and global temperatures, right? Every time carbon dioxide levels have gone up, global temperatures have increased. Please note, right, that the highest carbon dioxide concentration in the atmosphere going back 800,000 years is around 300 parts per million. Please note that we are over 340 parts per million now, right? And so we are in uncharted, unprecedented territory. This is what is ultimately responsible for our problems. Please note that temperature increase is a lagging phenomenon, right? So the carbon dioxide gets into the atmosphere. It takes 20, 50, 100 years for the temperature on the planet to actually increase as a result of the increased trapping of energy. That's why the UN has concluded that really we cannot meet the goal we've set for ourselves, the 1.5-degree goal, why we are going to overshoot it, even if we accomplish the most ambitious goal of getting to net zero carbon emissions by 2030. If we do overshoot it and then further reduce our emissions, the planet will correct, right? We will eventually come back down below 1.5 degrees. At least that's what the UN believes. To see this a little bit more up close, again, right? We are in completely uncharted territory in terms of carbon dioxide concentration, and we just keep going up and up. We are on a clear trend line that leads to disaster. Please note, this is one way of representing what the climate panel concluded. If we manage to limit climate change to around 1.5 degree, the little overshoot and then the correction, well, around 14% of the human population on the planet will be exposed to extreme heat on a twice a decade basis, every 5 years. But if we get up to 2 degrees, that goes up to more than a third of the human population. If we go up to 1.5 degrees, there will be very frequent mass mortalities of our coral reefs. Please note that coral reefs are the richest source of biodiversity in the planet, that 80% of the ocean's life spends part of its time in a coral reef. If we go up to 2 degrees, coral reefs will mostly disappear, says the UN, right? Similarly, plants and animals that will lose more than half their range, which makes it very likely that they will be subject to extinction. Under the 1.5 degree scenario, as you can see, 6% of insects, 8% of plants, 4% of vertebrates. Under the 2 degree scenario, it goes up to almost 20% of insects, 15% of plants, 10% of vertebrates, right? And so this is why it is so urgent that we act now in order to prevent these consequences that we can clearly anticipate. I've shown you this diagram before, but I want to really drill down on one of these multiple self-reinforcing cycles to conclude today's lecture. And part of what doing this over 4 weeks allows me to do is to go into a little bit more detail on one of these processes. So the basic idea here, and as you can see, there are multiple processes that this diagram tries to capture, where when we burn fossil fuel, when the air temperature increases as a result, it unleashes further processes that ultimately cause more increase in atmospheric temperature, that ultimately cause more heating. And so a self-reinforcing cycle here. The path I want to trace: fossil fuel heats the atmosphere, increases the temperature, that leads to Arctic ice cap melting. That in turn feeds back into a loss of global cooling from reflective ice albedo, right? And so we replace white with green and brown, and less of the sun's temperature energy reflects back out into the atmosphere and ultimately into space. As you can see, right, clouds are highly reflective. Fresh snow on ice is extremely reflective. Bare ice, quite reflective. Sea ice, quite reflective if that melts. And please note, right, the Antarctic is covered right now in mile high glaciers. That continent actually has the highest average elevation of any continent on Earth because there is so much ice sitting on it, right? If it melts, if it gives way to soil, that only reflects 5 to 30% of the sun's energy as opposed to 85 to 90%, right? Grass and crops reflect 10 to 25%, forests 5 to 20%. Again, you can do the math, you can see the difference, right? We're reducing the reflectivity of the surface of the earth by more than 50%. Similarly, oceans absorb a great deal of the heat. So that then means, among other things, that this big cycle that we rely on, the so-called Thermohelene cycle, in which the oceans of the world take warm water from the equator and push it to the poles, and in the turn, the poles cool that water and return it to the equatorial regions. A giant planetary air conditioning system has some implications that we had not anticipated up until this point, which are threatening the glaciers. I'm going to focus on Antarctica, right? A large continent. It's the 5th largest continent on the Earth, but if you include the ice shelves, it gets even bigger. And what this diagram shows you is these circulatory systems of water viewed from the perspective of the Antarctic. And what you're seeing with these blue arrows is cold, ancient water from the depths of the Pacific, the Atlantic, and the Indian Oceans being pulled slowly but surely to the Antarctic region, to the South Pole. What's pulling them there is winds that blow from the Arctic north, and that as they push the surface water away, create a vacuum, and that then pulls water from the depths further south and eventually surfaces that water around Antarctica. And this cycle is accelerating. It's accelerating because the energy in our atmosphere is increasing. These winds are getting stronger. As you can see, one of the things about Antarctica is there are no continents close to it. And so the winds really build strength over the oceans. And as the winds are strengthening, this cycle is accelerating and becoming more powerful. There are multiple issues to do with this. One of them is that the water from the depths of the ocean tends to be rich in carbon dioxide. Yeah, one of the phrases that a climate scientist uses to describe it is it contains the rot of ages, right? All this biological matter that has died and decayed and sunk to the bottom of the ocean is being pulled by these currents up to the surface of the ocean where carbon dioxide is released in the atmosphere. So if we are accelerating this process, we are potentially creating a further source, now not an anthropogenic, not a human caused source. It's not that we're burning oil, it's that the ocean is off gassing due to these up currents. And it's, on the other hand, anthropogenically generated climate change that is accelerating those currents, that is allowing those gases to escape. But there's an additional aspect to this, which is that the water that is being pulled to the south, to the Antarctic, is warm water. Remember, it originates in the equator. And so, what part of what's happening here is that the warm water is being pulled underneath the ice shelves and the glaciers, right? This is the land that is the base of the continent on which this ice is sitting. This is the South Ocean that surrounds Antarctica, and warm water is coming up under these glaciers, right? When Al Gore talked about the melting of the glaciers in his movie and book, An Inconvenient Truth, from 20 years ago, he anticipated that it would be heat from the Earth's atmosphere that would melt the ice shelves and glaciers, not warm water coming underneath. The warm water is more effective at conveying or transmitting the heat, and the fact that it's coming from the underside of the ice shelves and the glaciers, and this is a slightly more diagrammatic way to look at it, is causing two things to happen. On the one hand, this is called the grounding line, right? So this is a large glacier field. This is the point where it is anchored or connected to the continental shelf of the Antarctic, right? And this is called the calving line. This is the line at which, as the ice gets further and further out over the ocean, it tends to crack and fall into the ocean, creating icebergs. That's calving, right? When the ice falls off of the ice shelf into the ocean. Both the grounding line and the calving line are being pushed further back, and the result is destabilization of these ice fields. You may have seen the so-called Larsen ice fields in Antarctica are breaking up. They're divided into A, B, and C. A and B have now basically collapsed. C appears to be in the process of disintegrating. And it seems to be that this process is making that disintegration occur much more quickly than we had anticipated it would. Gore thought it wouldn't really happen until the end of this century. Here it is, 2022, happening already, right? And I want to add one more aspect to the process. And again, this is where Gore was half right. In Northern California, you're quite familiar with the idea of an atmospheric river, right? And this occurs, again, I'm a little out of my depth here, but I understand the basic outlines, which is when a high pressure and a low pressure zone interact in the right way. When the high pressure zone is very stable, it funnels the low pressure zone into a narrow channel, and the channel that it generates tends to move quickly, tends to be very high humidity, and to be sustained. And the result is that when that channel moves from the sea over land, it deposits a lot of rain very quickly in a concentrated area. It's not dispersed the way it might be if there weren't an atmospheric river. And it turns out, I can show you another image of this from space. This is actual satellite imagery from the Scripps Institution of Oceanography of an atmospheric river hitting Central America, coming out from the Pacific Ocean. When this occurs in the Antarctic, and this is increasingly occurring in the Antarctic, it further accelerates that process of destabilizing those ice shelves. I'll tell you very quickly a little story, and I'm to the point now of basically concluding today's lecture. There's a story from US Cold War history. We tried to build underground tunnels in Greenland to store and be able to move nuclear missiles around close or to the Soviet Union than the ones based in the continental United States. It was a vast, difficult project, drilling thousands of miles of tunnel through the Greenland ice fields. And it was a total failure. The reason it was a failure is because we did not recognize how fluid and mobile that ice is. The ice in the Antarctic and the Arctic, in Iceland and Greenland, is constantly moving. But having said that, those ice fields where the continent meets the ocean are big dams that keep the continental ice from moving into the ocean. As those ice fields decay and break and crumble and lose their integrity, there's nothing to stop that ice from moving to the ocean. Let me show you this to emphasize this point with you just a little bit more. You can see the slope, right? And I think it's even clearer in now, I guess it's clearest in this diagram, right? If these shelves break away, they serve kind of as a dam. More and more ice, this is why it's called an ice stream here, can move more and more quickly to the ocean. The Antarctic contains enough ice, right? The glaciers are in many places more than a mile high, that if it were all to melt, the world's oceans would be about 200 feet higher. And you can just think about where the world's cities are located, right? You might want to think about purchasing some property, I guess, in Geneva. There are not going to be too many places that are going to be above sea level if the world's oceans are 200 feet higher. Please note that the San Francisco Bay did not exist 10,000 years ago, right? What we think of as the bay was just a valley. The coastline was out where the Farallon Islands were, 20 miles out, right? Last time we had a big melt, guess what? The coast moved in 20 miles, that beautiful valley filled in and became that beautiful bay, right? We could be in for living in a dramatically different planet if we don't do something very quickly. All right, I'll stop there. Today was just trying to explain the core scientific processes as I understand them. Who wants to start us out with a question or a comment? Flossie, go ahead. Flossie, I'm sorry, you're still muted. You have to unmute yourself. Are you able to unmute yourself, Flossie? You probably got to hold.
I just did.
Yeah, okay, perfect.
I'm thinking that your lecture was brilliant, and I thank you for it. But it's also subversive. Pretty soon, this kind of lecture will be prohibited in the public high schools of Florida and Kansas and Montana. That's what I'm afraid of. We need this so badly now. Thank you.
Thank you, Flossie. And this is something that we will get into in further lectures. There are industries spending millions of dollars to muddy the water, to confuse us, to mislead us. There are political parties that are committed to do nothingism about this issue. Yeah. I think the hope, to the extent that there is hope, lies with the people who are out protesting right now. They're under 30 years old. They're saying, okay, this is our planet now, right? You guys are going to presumably be okay, but we're not if we continue on this path, and certainly our children won't. And so it does appear to me that increasingly they are having the urgent conversation with the executives of the oil companies, with the politicians who built their careers on denying this is real or man-made, or that there's anything we can do about it that would have any effect. And some of them, when they say, Grandpa, how can you do this to me, are getting through. And so slowly, I think we're seeing change in public opinion across the board. Let us hope it is fast enough for us to actually adapt. Bob, you have your hand up.
Thank you.
Yeah, a couple of comments of things that stood out to me in your lecture. First is the population. The first diagram that I saw that just took off was the population diagram. So perhaps the question is, why don't we reduce the population, which would help things? So, I'm not necessarily advocating that, but it's just a point that occurred to me because of what you were lecturing. Yeah. So, right, you go away. Where do you go? Okay, and then the second point is, so much of you talked about all of this energy, all of this stuff coming from the sun and causing changes in energy. We need to find better ways to capture that. I'm thinking of like a heat pump that somehow uses the increased temperature on the top of the earth to do other things. Go away.
Yeah, and so thank you, Bob. And I'm gonna maybe ask you to mute yourself, and I'll take your questions in turn, and then you can unmute and come back. The first comment, it's easy to speak in the abstract about having fewer human beings on the planet. There's another slide that I've shown you before that I'll just show you for a moment again. So if we get that 200-foot sea rise, right, this is what that does to Europe, right? This is continental Europe today, with the land that currently sustains 420 million people. This is continental Europe, or as these artists Helen and Newton Harrison call it, Peninsula Europe, after 4 degrees Celsius temperature rise and the increase by 200 feet of the sea level. And this is a continent that can sustain 45 million people. So that means, right, over 350 million people have perished or become refugees, climate refugees, as a result of the rising sea levels, right? And so the problem with climate-caused depopulation is that it is too late, right? In a sense, the worst has already happened by the time we get to climate change producing the result we need. I happen to believe that the demographic evidence seems to suggest that human population growth is actually slowing dramatically, and that by the end of the century, we will be very close to steady state at around 9, it's guesswork, give or take a billion, 9 billion people on the planet, right? And I'm also of the opinion that with the right technological as well as ethical changes, we actually can sustain that number of people. And frankly, as we become richer, as we become more secure that our children will survive and that we don't need their labor to sustain us in our retirement, then people have fewer children. So we may actually see a reverse in the population growth trends. We're never going to get back to a billion, but we might see it come back down to 7 billion another century out, 2200, right? But having said that, I think your second suggestion really points in the right direction, which is to say we need to get creative quickly, and solar energy combined with heat pumps, which is, for what it's worth, what I have on my house, is a really good and effective approach, right? It's just the beginning, but yes, we do need to figure out how to use the solar energy. I've been fantasizing about the idea. This is not just my idea, but my little tweak is to do it with solar energy. There's a so-called geoengineering project at Harvard University. Bill Gates has funded it. They've got a team of scientists looking at things that we can do to do our best to mitigate or reverse climate change. And Matt has spoken with us about the idea of putting material into the stratosphere that reflects the sun's energy back out. It's kind of like tinting the windows that we've rolled up on the planet. Another proposal, which I think is a really interesting proposal, is to put ships with large pumps and motors into the Antarctic and Arctic to help regenerate the ice that's being lost, to rebuild the glaciers, to, in other words, create artificial snowstorms and a greater accumulation of snow over the winter. Why not do that with solar energy? Right? I mean, one of the problems we run into with all these geoengineering schemes is they tend to take a lot of energy to actually do. But yes, I agree, Bob, that we need creative, out-of-the-box engineering approaches to this. In order to get there, we don't need a political philosopher sitting in his study cooking up his harebrained schemes. We need research scientists doing serious fundamental science work and experiments. What does that mean we need? It means we need a large investment in research and development. And I think one of the real shames of the fact that the Build Back Better bill didn't get passed is that it had billions of dollars for R&D in alternative energy and approaches to using less energy in our everyday living and production processes. So I think you're barking up exactly the right tree. And if we can really become innovative and concerted about this, we can do this without having mass fatality events, and obviously a better world. Matt, I dragged you into it. Do you have any comments or thoughts today?
Yeah, all I could say is, what do you mean by we, pale-face? I mean, this is something where you'd like to think that the people of the world would get together and do something intelligent. There are people who don't work quite that way. I mean, we've just seen a major nation, one of the largest creators of carbon dioxide, just disregard all international law and all common sense and start a war with another country. I mean, this is unbelievable, and yet it happens.
Yeah,
I think that, as I've said before, I think the probability is that one nation will make a decision to do the geoengineering thing, and everybody else be damned. And they may be very successful for the benefit of the entire world, and they may cause huge problems that we don't foresee. But it's not something that everybody has to be on board with. This is something that can be attacked in perhaps a very unsatisfactory way by a single nation. That's all I have. That's my comment for today.
Thank you, Matt. And I'll just point out, why limit yourself to a nation, right? We've got Elon Musk and Jeff Bezos shooting themselves up into space. They can build the technology to do this. When we're in a world where there are people with tens or hundreds of billions of dollars, they become almost as powerful as nations. So yes, on the one hand, who's the we, right? The we who faces the problem is the human species, where there is, it seems to be for the first time in human history, a greater likelihood that we will go extinct than that we will survive. And that we will go extinct because we create the events that extinguish us. And please note, this is slow violence, right? This is not somebody flipping a switch that launches a nuclear attack and it's over in a matter of hours. This is a process that takes centuries and involves centuries of anarchy, chaos, Hobbesian state of nature kind of affairs occurring on the planet Earth. And so we are all at risk, and we are all involved in causal processes that create this. And yet the capacity for collective action required to address it does not exist, right? And so, yeah, Matt, you've put your finger on the problem, and that's what tempts countries or individuals to unilateral action. I am inclined to believe that exemplary leadership, which is also unilateral, could begin a more virtuous cycle. If the United States can show, if Germany can show, if Japan can show that this can be done, that we can get to net zero and maintain something like the standard of living that we like, that we can get to net zero, and who knows, maybe even in many respects benefit from it, then maybe many other countries will follow. And by the way, if those people under 30 who are banging those drums and saying, we got to act now, begin to rise to power, then in addition to us exemplifying that this can be done, we might actually start funding it in the parts of the world that are really put in an untenable position right now, where they have to choose between development in order to bring their citizens into modernity and contributing to climate change. I'm seeing in the chat bar, I guess most of you are seeing it also, from David Pearson, that you have a group, a subcommittee there that's working on these issues and working with Bill McKibben's third act, right, which, as most of you must know already, is designed to allow people who are retired or seniors, I forget what the exact age threshold is, I don't think I'm there yet, to come together and try to pressure for change on this issue, right? Baby boomers have been the most effective political generation of the 20th century. Might this be their swan song, their most important contribution to our politics, especially if the baby boomers and the current people under 30 align on this? There's much greater prospects for change. That's getting us ahead into the politics of this, which is where I want to go in a few weeks. Anybody else with a final comment for today? All right.
David, I'd just like to agree with your optimism that if, for instance, we develop it here in the develop some technology here in the United States and altruistically share it with the rest of the world, that's one of the ways to, so everybody doesn't have to do all the development. Somebody's can get it done and share it.
Yeah, great thought to conclude on. Thank you, Bob. Thank you, everybody. Take care, be well, more to follow. See you next week. Thanks, bye-bye.